In our last video, we learned about matrix multiplication happening column-wise. So specifically, what I meant by that is that if you wanted to do a matrix product AB, and if it was okay to do that because the number of columns of A was the same as the number of rows of B, then what you could do is think about that product one column at a time, in the sense that if you give the columns of B names, so you call the first column D1 and the second column D2, and the last column, let's say DP, so these D's are height n column vectors, then the result could be obtained by making the matrix whose first column was A times the first column of B, and whose second column was A times the second column of B, and whose last column was A times the last column of B. So that's the sense in which matrix multiplication works column-wise. You can work out the product by multiplying A into the columns of B one column at a time. And if something is true about the columns of a matrix, then it ought to be, in some sense, true about the rows of a matrix. So in this video, we're going to see how matrix multiplication can be also thought of as happening one column at a time. But to begin this investigation, what we're going to look at is what happens when we multiply row vectors into matrices. So here I'm going to have a row vector A, so this is a 1 by 3 row vector, and I'm going to have a matrix B, and my matrix is 3 by 2. So the result of this multiplication is going to be a 1 by 2 row vector. And if you remember how you work these out, well, then you multiply the row of A into the columns of B one at a time. So if you look at what you get, the 1, 1 entry will be obtained by multiplying the first row of A into the first column of B. So you get XA plus YC plus ZE. And the 1, 2 entry will be the first row of A times the second column of B. So that's XB plus YD plus ZF. But we can rewrite this, because if we take out the x's, and look what the x's are multiplied by, you have x times AB, the 1 by 2 row vector AB, plus y times CD, plus z times EF. And what are these 1 by 2 row vectors? Those are the rows of B. Right, so if you look here at the first row of B, then that was AB, so that's the thing which appears here. And if you look at the second row of B, CD, that's the thing here. And if you look at the last row, EF, then that is what we got here. So when we did this multiplication, when we multiplied a row vector A into a matrix B, the result was a linear combination of the rows of B, and the coefficients in that linear combination were the entries in our row vector. So remember what a linear combination means. A linear combination of some vectors is when you multiply those vectors by scalars and then add up the results. So here we have a scalar x times the row vector AB plus another scalar y times the row vector CD plus another scalar z times the row vector EF. That's called a linear combination of the rows of B. So let's write this down. This is a linear combination of the rows of the matrix B. When you multiply a row vector into a matrix, the result is a linear combination of the rows of that matrix. So let's spell this out in general. So in general, you take a 1 by n row vector A, and you call the entries A1, A2, A3 up to AN. And you take an n by p matrix B, so that it's okay to do the matrix multiplication A times B. And you give names to the rows of B, so let's call them S1, S2 up to Sn. Then the product A times B is equal to a linear combination of those rows, where the scalars in those linear combinations and the scalars in that linear combination are the entries of the row vector A. So just to spell out what's going on with this notation, so in our example above, the rows would be, well, S1 would be the first row of B, which was the 1 by 2 row vector AB, and S2 would be the second row of B, which is the row vector CD, and S3 would be equal to EF. And in general, what's happening is when you multiply a row vector into a matrix, the result is a linear combination of the rows of the matrix. So let's look now at, in general, the sense in which matrix multiplication happens row-wise. So we're going to return to another example. This is an example, this example here, where we look at a product of a 2 by 3 matrix and a 3 by 2 matrix. Let's call them as usual, the first one A and the second one B, and the result when we multiply them ought to be 2 by 2. And if you think about working out this matrix product, what would happen when we tried to work out the first row of the answer? So we want to work out this row here. How do we do that? Well, when we do this, we only need to think about the first row of A, because the entries in the matrix product, and the entries in the first row of the matrix product, AB, come from multiplying the first row into the columns of B. So the 1, 1 entry will be the first row of A times the second column, the first column of B. The 1, 2 entry will be the first row of A times the second column of B. But when we work out that first row, we only ever use the first row of A. So if you write down what you have there, if we call the first row of A R1, so R1 is A, B, C, and R2, the second row of A, would be D, E, F. Then what you get when you do this matrix product is in the first row, you've got R1 times B. Okay, I'm going to draw these lines to mean that the first row of this matrix product is R1 times B. And the second row will be the second row of A times B. This is true always. This is true in general. So if you have any m by n matrix, and you call the rows of that matrix R1, R2, R3 up to Rm, and you let B be any n by p matrix, so that the matrix product AB is legitimate, it makes sense, then the matrix product AB is the matrix whose first row is obtained by multiplying the first row of A into B. So R1B, like this. And the second row is obtained by multiplying the second row of A into B, and so on. And the last row will be multiplying the last row of A into B. So what can we get out of this? What can we get out of this fact that we can think of matrix multiplication happening row-wise? Well, we know that in general, RB, for a row vector R, is a linear combination of the rows of B. Therefore, the rows of AB are all linear combinations of the rows of B. So that's interesting because it gives us two different ways of thinking about this product A and B, A times B. We saw before that the columns of AB were linear combinations of the columns of A, and now we've seen that the rows of AB are linear combinations of the rows of B. Okay, so I should say that in the last couple of videos I've stated these theorems about rows and columns without giving a full proof using the matrix entries. If you want to see those full proofs, you can of course find them written down in the lecture notes for this section. I think they're the kind of thing which are a little bit easier to understand rather than when somebody talks about them, to actually be able to see these written down on paper.